Good afternoon, everyone. My name is Di Chen. Today I'm going to talk about the in situ thermal conductivity measurement of silicon carbide composite. In this talk, I'm going to introduce an innovative technique that can measure the thermal conductivity during the ion irradiation. Before that, let me introduce myself. Currently, I'm a research assistant professor in University of Houston, Department of Physics. My research interests are nuclear materials under extreme conditions, defect engineering, and the fundamental understanding of radiation damage evolution. Another author of this talk is Piyush, who is from Idaho National Lab. And all the silicon carbide composite samples we were using are from a company called General Atomics. And this project is supported by DOE Versatile Test Reactor Program. As we know that people are pursuing the next generation nuclear reactor concepts. This figure shows the environment for the different types of nuclear reactors. As you can see that for the traditional generation 2 and the generation 3 nuclear reactors, the temperature and the radiation damage are acceptable. However, when you are talking about the advanced reactor concepts, you will see that the temperature could be above 1000 C and the radiation damage could be more than 200 dPa. Therefore, the traditional nuclear materials that can be used in the generation 2 and the generation 3 nuclear reactors cannot even survive in such harsh environment. So it is critical and necessary to develop new types of nuclear materials. In order to develop such kind of materials, we need powerful tool, and the ion beam is one of them. This figure shows the time required for accumulating 10 dPa radiation damage for ion radiation and the neutron radiation. For the neutron radiation, we can see that if you are talking about the lead water reactor, it's going to take 10 years. And for the high flux thermal test reactor, it's going to take 3 years. And even for the fast reactor, the time required is around 6 months. Well, for the ion beam radiation, the time required is much shorter. For example, for the proton radiation, if you want to accumulate 10 dPa radiation damage, it's going to take only 20 days. And for the soft ion radiation, which is much more impressive, the time required is only 5 hours. So as you can see that ion beam radiation has been used as a surrogate to investigate the radiation effect in materials for decades. Its advantages are pretty obvious: higher flux, higher fluence, and significantly reduce the cost and the time of the experiment for sure. Well, not a complete surrogate for neutron radiation, it does allow the explosion of potential microstructure states and their influence on properties. We know that ion radiation is not the substitution of neutron radiation, but it can do a lot of things. For example, we can use ion radiation to test and eliminate the candidates that are not durable and reliable under radiation. If the sample cannot survive under ion radiation, and we believe that it could not be used in the neutron irradiation environment. Also, ion radiation can help us to reveal the mechanism of radiation damage in a simple and easy way as well. Okay, silicon carbide. Silicon carbide is one of the most important, nuclear materials that can be potentially used in the next generation nuclear reactors. And the silicon carbide has been used widely for the industrial purposes more than 100 years already. Its high hardness and the ability to survive high temperature and excellent oxidation resistance make it ideal for demanding applications such as cutting tools and high power electrical system. And it has also been used for the certain nuclear energy applications such as coating tracer particles and cladding materials. And this figure shows the structure of typical tracer particle. As you can see that one shell of the tracer particle is made of silicon carbide. However, the monolithic and the pure silicon carbide is very fragile and easy to break. And its brittleness limits its use as the structural materials. But the good thing is that people came up with an idea to fabricate silicon carbide composite by reinforcing the monolithic silicon carbide with silicon carbide fibers. As you can see, in this stress curve, the monolithic silicon carbide is very fragile and easy to break, but the silicon carbide composite, becomes much more ductile. And all the silicon carbide composite sample we were using are from General Atomics. General Atomics is a professional company that can fabricate silicon carbide composite, and they can just make silicon carbide composite cladding and other components for the nuclear energy purposes. Okay, for the ion-radiation experiment. As we mentioned above, the self-ion can just give you the most efficient way of generating radiation damage. So we selected carbon ion to bombard the silicon carbide composite. Before performing the ion radiation experiment, we did a trim calculation, as you can see in the left figure. And you can see the distribution of the radiation damage is not uniform. But from previous study, we can see that if you are talking about the low energy implantation, you're going to get the amorphous region. And although you can just anneal the sample at high temperature to repair the amorphous structure to some extent, but it looks like the amorphous structure is pretty stable. So in order to simplify the question, we just average the radiation damage to some extent, which we believe that is the easy way to just get the radiation damage and correlate it to the thermal property. This demonstrated the overview of the 1.7 MV tandem accelerator at IBM lab of University of Houston. And you can see that this tandem accelerator is able to generate most elements and isotopes covering the energy from a few tens keV to over 10 MeV. And this is the side view of the tandem accelerator. And specifically, we have a special designed high temperature heating stage, which can heat up the sample up to 1800 C, which is very high temperature. The purpose of such high temperature is to simulate the harsh environment in the advanced nuclear reactor concept. Okay. This is the methodology of the in-situ thermal property measurement. As you can see, is the overview and the set view of this tandem accelerator, and it's going to work this way. This, instead of measuring the thermal property in a traditional way, and our method combines the ion radiation, laser beam, and the infrared camera. Okay, it works this way. When you just shoot the laser on the surface of the sample, it will just form a very tiny hot spot. Therefore, you are going to get a temperature distribution on the surface of the sample. This temperature distribution information can be observed and obtained by a high resolution infrared camera. And by analyzing the temperature gradient, you should be able to get the thermal conductivity. Okay. Here is the comparison of Situ, irradiation and in-situ radiation. For the Situ radiation, is the flow chart. The flow chart shows that first you need to do the beam radiation over the entire sample, and you take the sample out after the implantation to do the thermal property measurement. And after that, you are going to get one data point, right? And if you want to get the trend of the thermal conductivity as a function of radiation, you need to repeat it again to get the thermal property for another fluids. So you have to move to the next cycle. And you are going to get the second data point, and again you are going to get the entire curve, which is going to take weeks, months, or even years. And for the in-situ measurement, you don't have to go to that complicated process. What you need to do is similarly, you need to just irradiate the sample by the traditional way, but simultaneously, you need to just measure the thermal property during the radiation. Therefore, after you just complete the radiation damage experiment, you're going to get a complete curve for the multiple fluids, which just save a lot of time and make it much more efficient. And this demonstrates the setup of our in-situ thermal property measurement system, showing the location of our camera, laser, and the chamber which contains the sample stage inside. As you can see, when the ion beam radiation is being performed, and on one side, the laser is going to just the laser source is going to shoot the laser and focus on the surface of the sample. And the angle between the laser and the ion beam is around 45 degrees. And on the other side, and the air camera is going to capture the temperature information from the surface of the sample in a symmetry way. Okay, this is the closed loop of the laser source and the air camera. You can see what it looks like when you turn the laser on, and you can see the laser is a high power laser with the power 3 watts, and also the lace in between the laser and the chamber focuses the beam, focuses the laser, to a tiny spot on the surface of the sample. And on the other side, you can see the air camera, and the left figure. The red figure, shows we have successfully demonstrated the temperature gradient on the standard silicon carbide, and it is validated this method, and for sure that we are able to get the thermal, we are able to get the temperature, gradient from the laser hitting the sample. Okay. After this initial testing, we just move forward to the next step. We use the silicon carbide composite sample from General Atomics to do the measurement. Let's see that General Atomics provided us two different types of samples. One is polished, one is unpolished. So the middle figure shows the image for the silicon carbide composite manufactured by the General Atomics at room temperature hit by the laser beam. And in the middle, the bright spot, the tiny bright spot is the exact laser spot. And the red figure shows the experimental temperature distribution, captured by the air camera. The next question, the next slide shows the movie we captured by the air camera. We captured by using the air camera, showing what it looks like when the beam on and the beam off. See, when the laser beam is on, you can see the hot spot at center, and when the beam off, you can see the hot spot is gone. Okay. the next question is how to calculate the thermal conductivity. Since we have already known the temperature gradient by using the laser beam, we are supposed to use the heat transfer equation to get the thermal conductivity. And in this calculation, we use the boundary condition to consider the contribution of the black body radiation as well. So you can see in this equation, and the boundary condition is at z equal to 0, which means the surface of silicon carbide. The T is the temperature of the sample surface, and the Q source is the energy input rate per unit volume. And the rho is the density of the sample material, and the epsilon is the surface emissivity, and the sigma is the Boltzmann constant, and the C is the heat capacity, and the T ambience is the ambient temperature. The ideal case is you can just you can get the thermal conductivity by inputting all the parameters, but in reality you may not just get them in one time, but still it's okay because you can just get the relative change of the thermal conductivity, and if you calibrate the thermal conductivity at the first place, you are still able to get the thermal conductivity as function of the radiation. Okay, in order to fit the experimental curve, we use the heat transfer equation to just get the simulated curve, as you can see, in the bottom figures. Okay, at the last, I want to just emphasize the result we obtained from the in situ thermal property measurement. And the left figure shows the previous studies, on the silicon carbide composite. So those curves are from different studies, and this also summarizes all the data previously, and those data shows rapid decrease and the saturation in thermal conductivity, as you can see if you focus on the top part of this figure. You know that this work took almost years to get all the data points, and our work, as you can see in the red figure, this is the first time we got the relative thermal conductivity of the silicon carbide composite as a function of ion radiation. You see, we got a similar trend of the in agreement with the previous study, but the time we use is only 5 hours. So you see how efficient of using this innovative technique to get the result. Also, there's another feature that I want to emphasize is that the turnaround point is around 0.1 dPa, as you can see, and we got the similar result, which validated our results as well. So it's proof that our technique works pretty well. And finally, let me summarize my talk. In my presentation, a unique in situ thermal property measurement technique coupling with ion radiation, laser beam, and the infrared detection has been developed to investigate the influence of radiation in a much efficient manner. Okay, and we performed the in situ thermal conductivity measurement on silicon carbide composite. And we found that the ion radiation leads rapid decrease and the saturation in thermal conductivity, which is in agreement with the trend observed by ex situ experiment. So thank you for your attendance. And if you are interested in this technique or you want to just perform some extra high temperature irradiation, please feel free to contact me. Okay, thank you.